Here is a graph showing how we solve AX equals to B with LU decomposition. After getting the decomposition of A with L and U, we first construct an intermediate variable D, which equals to U times X. And with this D, we first solve the first linear system and get the values of D. And then we solve the second linear system and finally have the values of our solution X. Before going into detail of how we're going to treat an arbitrary matrix, let's first look at a special case where the matrices are symmetric. In this case, we are going to use a method called Cholesky decomposition. For many symmetric matrices, A can be decomposed into the product of a lower triangular matrix and its transpose. In this case, the upper triangular matrix is now the transpose of the lower triangular matrix. To perform the decomposition, all we need is to find the values for the L's. With this decomposed L and L transpose, we will first replace A with L times L transpose and then build an intermediate variable D, which equals to L transpose times X. And with this intermediate D, we first solve this linear system to find the values of D and finally solve the second linear system to have our solution. Now let's look at how we compute every values in the L matrix. This is A, this is L, and this is L transpose. We are going to build equations based on how we compute every values in the matrix A, from left to right, from top to bottom. To compute A11, we need information from the first row of L and the first column of L transpose. This is in here. And to compute A12, we need the second row in L and the first column in L transpose. And to compute A13, we need the third row in L and the first column in L transpose. And with these three equations, we compute Li11 and L21 and L31. And second, we build equations based on how we compute the second column of A, as listed here. And so on and so forth. We find the general form of computing all the L's are here. We notice that we are taking a square root of something. If they are taking a square root of a negative value, then the algorithm will fail. So how do we limit the matrix A such that we are always taking the square root if positive? It turns out that if we have another condition on A, which is asking the A to be positive definite, then we are guaranteed that we are always taking square root of non-negative values. So with this newly added condition, the Cholesky decomposition can be described as following. Cholesky decomposition is a decomposition of A into the product of a lower triangular matrix and its transpose. So here are some notes of this Cholesky decomposition. First, running time. It turns out that we need 1/6 times n cubed multiplications and the same number of additions. See here, the running time is still cubic, but it has a lower constant as opposed to the previous n cubed. Furthermore, because L matrix and U matrix share the same parameters, so we only need half as much computation and storage than a general form LU decomposition. And this Cholesky decomposition turns out to be a preferred method for solving symmetric positive definite systems. So now let's look at the general form of LU decomposition. After factoring A into L times U, we construct an intermediate variable y as u times x. And now we first solve this linear system and then use the solution of y to solve the second linear equation. And from the previous slides of forward and backward substitution, we know the last two steps it needs running time of n squared. So the total time of using LU decomposition to solve this linear system is dominated by the matrix decomposition step. Now let's have a closer look of the matrix decomposition. Given a matrix of size n, so here n is equal to 3, we have n squared equations. But for the unknowns, we have in total n squared plus n unknowns. So the number of unknowns is larger than the number of equations we have. In other words, we are faced with an under-constraint problem. So ways to treat this include a Doolittle's method that explicitly requires all the diagonal values of matrix L to be 1. And there is another similar way called Kraut's method that requires all the diagonals in the matrix U are 1. So let's look at the example of Doolittle's method. With this, we can see all the diagonals of matrix L are 1. So this is A, this is L, and this is U. Similar to the workflow that we used for the Cholesky decomposition. Still, we now build equations of computing A from left to right, from top to bottom. So because we have explicitly assigned value of 1 to the diagonals of in L, so now the A11 is equal to first row times first column, which is U11. And we further build equations to solve to A21 and A31. And then with this, we can solve for L21 and L31. And next is to find values of the second column of U and the second column of L, as here. And finally, we can write these into a general form as following. So we loop over I from 1 to n, and for every fixed one, I, we loop over j from 1 to I to solve uji, and from I plus 1 to n to solve lji. And this is the general form of LU decomposition with the Doolittle's factorization to solve the matrix L and matrix U. And there are several interesting notes. First, we find the number of outputs is the same as number of inputs. Look at here. We have n squared of inputs, and after the decomposition, we find the number of L's that are not ones are the same as the number of zeros in this upper triangular matrix. So, in fact, all the unknowns in L and all the unknowns in U can be put together into a single matrix. And the total number of them is also n squared. So that's why we say the number of outputs is the same as number of input. Furthermore, this algorithm only refers to elements of A, not B. See here, to solve U, we only need known values in A and the previously solved values in L and U, and same for solving the L's. So with these interesting notes, we find actually we can do this algorithm in place. So we can gradually replace the values in A with the L and U values in the matrix L and matrix U. And the resulting matrix after this in-place algorithm, note that it cannot be interpreted as a regular matrix. It should be mapped back into the original L matrix and U matrix. with the 0 and 1 added. And we can further rewrite the forward and backward substitution routines to leverage this packed LU matrix where we do in-place computation. And still, the running time is about 1/3 times n cubed multiplies in same number of s. And note that this decomposition is independent of the right-hand side. And from the previous slides of back and forward substitution, we know the right-hand side takes n squared running time. So this LU decomposition is the preferred general method for solving linear equations. We also note that pivoting is very important. Partial pivoting is sufficient and are widely implemented in some decomposition methods. So from these introduced LU decomposition methods, we find LU with pivoting can succeed even if matrix is singular. However, from the previous slides, we have already known that backward or forward substitution will fail if the matrix is singular. So that's all about LU decomposition. Hope you enjoy it.